In this section, we'll work through 2 sample AP problems that relate to electrochemistry. The following questions refer to the electrochemical cell shown, the silver zinc cell. Part A says write a balanced net ionic equation for the spontaneous reaction that takes place in the cell. And Part B, given the following values, calculate the standard cell potential, E0, for the reaction that you write in Part A. So we're given the standard reduction potentials for zinc and silver. And so we can determine what is oxidized and what is reduced. So the reduction happens at the silver, and the oxidation happens at the zinc. So reduction happens at the cathode, so this is the cathode, and zinc then is the anode. Okay, so take a minute to try and combine these 2 equations to write the net ionic equation, and then I'll show you. So I need to flip this top reaction so that I'm seeing oxidation or a loss of electrons. So zinc, then I have zinc 2 plus, and 2 electrons. And the second equation I need to double so that I'm gaining the same number of electrons as I'm losing. So I have 2 Ag plus zinc solid. Then electrons gained and lost are the same. So I have zinc 2 plus 2 Ag solid. Okay. So there's my balanced net ionic equation. Okay, balanced for both matter and charge. Then I need to calculate the E0. So E0 is cathode minus anode, or reduction minus oxidation. So 0.80 volts minus negative 0.76 volts. And that is, 1.56 volts. Okay, so there's parts A and B. Here's the fully worked out solution for A and B, in addition to what I showed you. Now part C says label the anode and cathode. D says determine the concentration of silver nitrate and the concentration of zinc nitrate that are needed to generate that cell potential. And then how will the cell potential be affected if potassium iodide is added to the silver half of the cell? Justify your answer. Okay, so I had already labeled the cathode and anode previously, but the anode is where the oxidation occurs, which we said was here, and the cathode is where the reduction occurs, which we said was at the silver. Okay, so there's part C. Now part D, determine the concentration of silver nitrate and the concentration of zinc nitrate that are needed to generate a cell potential that we calculated previously. Now, because we're talking about a standard cell potential, electric cell potential, both concentrations have to be 1 molar, because that is the standard conditions for standard cell potential. And then finally, part E, how will the cell potential be affected if potassium iodide is added to the silver half of the cell? If potassium iodide is added, then these silver ions that are here from the silver nitrate are going to form a precipitate with the iodine ion. So we're going to have silver iodide precipitate in the bottom of this solution, okay, which will affect the ability for the electrons to be gained at this cathode. So we can say a precipitate will form as iodide ions react with silver plus ions in solution on the left side by the cathode. And so the concentration of the silver plus will be reduced, which causes the cell potential to decrease. Sample AP free response question 2. A student wants to find out the concentration of hydrogen peroxide H2O2 in a solution of H2O2. The student can use one of two titrants, the dichromate ion, Cr2O7 2-, or the cobalt 2 ion, CO2+. The balanced equations for the two titration reactions and the half reactions and cell potential values for the systems related to the titrations are given on the next slide. So if I use dichromate as a titrant, I have that reaction shown, dichromate titrated with the hydrogen peroxide, or the cobalt 2+ ion titrated. Okay, so here's the half reaction for the cobalt, for the hydrogen peroxide, for the dichromate, and for this oxygen gas going to H2O2. Okay, part A, use the information in the table to calculate the following. The cell potential for the reaction between the dichromate and the hydrogen peroxide at 298 Kelvin, and the cell potential for the reaction between the cobalt 2+ and the hydrogen peroxide at 298 Kelvin. So try to do that on your own first, then I'll walk you through a step-by-step solution. Okay, so in order to do this, I just had to go back and look up the cell potentials for the chromate and the hydrogen peroxide and the cobalt to find the cell potential. So I get 1.33 minus 0.70 for the dichromate and hydrogen peroxide, and I get minus 1.84 plus 1.77 for the cobalt and the hydrogen peroxide, which is minus 0.07. Now, part B says, based on those calculated values, the student has to choose the titrant for which the titration reaction is thermodynamically favorable. So, part 1, which titrant should the student use, and explain your reasoning. Part 2, calculate the value of delta G in kilojoules per mole for the reaction between the chosen titrant and the H2O2. Okay, so which titrant should the student use? The student should use the dichromate ion because you get a positive cell potential for that reaction, which means the reaction is thermodynamically favorable. We can calculate delta G using our equation minus N times F times the cell potential. And so I have 6 moles of electrons in the balanced reaction for the dichromate ion times my Faraday's constant in coulombs per mole, times the 0.63 joules per coulomb, or volts, that I calculated to find my cell potential. And then I just need to convert from joules to kilojoules. There's 1,000 joules in 1 kilojoule. And so I get a Gibbs free energy, a delta G of a negative 360 kilojoules per mole. And again, I get a negative delta G, which supports my answer to part 1, saying that this reaction is spontaneous and therefore thermodynamically favorable.